Welcome to Photovoltaic Thermal Systems training. This training is a part of European Solarize project that focus on the adoption of solar energy in the 2Cs region. The training will focus on PVT systems, their applications, barriers, and future developments and opportunities. A PVT system combines photovoltaic module and solar thermal module into one integrated unit. It provides low-carbon electricity and heat from same renewable energy source at the same time. The electricity is produced by solar cells and the waste heat is extracted using a thermal module. These systems offer numerous advantages. The fluid flowing under the PV module reduces cell temperature, which results in a better PV efficiency. PVT is more convenient for those with limited roof area. Mostly air or water are used as heat extraction medium, which are found abundantly. These systems works in all temperature. They have low operating and maintenance cost. The disadvantages include they have high investment cost, less efficient during the winter season. These systems are still not popular despite they offer many benefits. Engineers face technical problems in the design because of the complexity. Heat transfer medium plays a vital role in heat extraction. Typically it is air or liquid that flows at the back of the panel. This liquid can be water, some phase change material, or water mixed with glycol. In air-based PVT systems, cold air is injected from one end and warm air is collected from other side. These systems have no corrosion, leaking, or boiling issues. The drawback is they have low heat transfer because of low heat capacity and low thermal conductivity. In water-based, they are the most common used panels for domestic heating purposes. The cold water is injected from one side and warm water is collected from other end of the panel. In order to avoid freezing, glycol is mixed with water in northern regions. The flow passage for the liquid-based collector can be in a shape of oscillatory flow, serpentine flow, web flow, parallel flow, or parallel serpentine flow. Similarly, air-based collectors are subdivided into various categories on the basis of airflow pattern. In the first one, air runs below the PV module. Here, air is injected above the PV module and is collected from under the PV module. In dual channel, air runs above and below the PV module in parallel. This double pass collector is opposite to the one shown in figure B. Lastly, fins are attached in an air channel to improve heat transfer rate. Moreover, there is a bifluid shown in figure 5 where both air and liquid are used simultaneously, thereby enhancing heat transfer. These systems have several applications and are divided according to their temperatures. Low temperature applications require temperature up to 50 degrees Celsius. Medium temperature applications require temperature between 50 to 80 degrees Celsius, and high temperature application requires temperature more than 80 degrees Celsius. Today, one of the most common technologies of PVT is building integrated PVT systems that are mounted on the walls, occupies less space, and provides better efficiency. Drying is very common in developing countries for preservation of agricultural products and food, and these dried products are good source of nutrients. A process of removing mineral components from saline water using solar radiation is desalination, which can be used for human consumption or irrigation. Thermal desalination requires high temperature and can be useful in remote areas and isolated islands. Another interesting application of PVT system is district heating and cooling, which requires large space. Mostly parabolic trough collectors are used for this, and this can be useful for regions such as Mediterranean, Gulf and South Asia. Heat produced by the PVT is used for heating during winter season, but it gets wasted during summer season. This heat can be used for cooling purpose by integrating a chiller and a control unit. Trigeneration and refrigeration are another possible applications of PVTs. These applications are in early stages. Hot water, electricity, and space cooling is generated in trigeneration, whereas in refrigeration can be used for medical labs, marts, and isolated regions. In a PVT, we have two mathematical models. One is based on energy conservation principle. An electrical model is built using Shockley-Diode equation. A nonlinear model, which is a function of state x, control input u, and non-control inputs w. The state x contains temperatures of the PVT collector layers, and we can have 4 to 7 states depending on the model. Control input, which is mass flow rate, and the uncontrolled inputs, which are solar radiation, ambient temperature, and wind speed. The output Y, which is outlet temperature of the fluid, and we have electric power, which is output of electrical model. Design and physical parameters are optimized using optimization tool to design a new PVT, and thermal and electrical outputs are maximized. It is necessary to have a control to guarantee desired temperature depending on the application. The PV efficiency highly depends on cell temperature, and a rise of 2 degrees Celsius temperature degrades PV efficiency by 1%. The addition of a glass cover increases module's temperature, which leads to lower PV efficiency. Currently, these systems offer 40% thermal and between 15 to 22% electrical efficiency. It is possible to achieve 80% thermal efficiency in future. The average price of a collector is €350 per meter square, depending on the region. The cost of PVT is 1.5 to 2 times higher than equivalent PV system and 1 to 1.5 times higher than equivalent solar thermal module. Since 2005, the prices fall due to decline in PV prices and are expected to decline further in future. The main barriers are either in technical or economic domain. These barriers include low deployment of PVTs compared with PV or solar thermal systems alone, not capturing a new market. The payback time is long, approximately 15 to 21 years. The awareness of the technology is still low for both consumers and installers. PVT systems combine PV and solar thermal modules, which increases the complexity of the system compared to PV and solar thermal system alone. Another major factor is reliability. Some remaining challenges that may be solved in future are protection against heating, improving economics, and reducing heat losses. Integration of heat pump and development in thermal storage will assist the growth of PVT market. The opportunities include combination of PVT with heat pump to reach near zero energy residential building, heat pump and refrigeration coupled with PVT for space heating and cooling depending on the season, higher combined thermal and electrical yield per square meter. The combined efficiency of PVT is higher than PV and solar thermal system alone. The use of PVT systems is marginal, especially in industries where they can cover both electrical and thermal demand. The complex system design due to integration of PV and solar thermal module is a major barrier. Thank you for your time.